Hello, everybody. Okay, so in this video, we are just looking at future values, or like when we're dealing with problems involving like savings accounts or like investment accounts in financial maths. So, say we have like a savings account where we put like €500 in every month, right? So we have a recurring payment in this savings account, and I want to find out how much is this account worth in like 30 years' time? Well, we have to remember is, right? It's like 30 years' time. 30 years' time, that first payment you put in will accrue interest for that full 30 years. But that last payment you put in would only accrue interest for that one interest period. So we have now like multiple different payments, all of um different compounding like interests, stuff like that. So if we save a constant amount at the start of each month, so at the start of each month over a number of years, each installment will earn a different amount of compound interest. So, e.g., looking at the future values of each installment after 3 years. So here is a monthly installment over 3 years. So this here will be my first payment, because you see here, it will accrue interest for that full 36 months. It will accrue interest for that full 3-year period. And then my last installment is here because it will only accrue interest for that final month, okay? So what we notice here is I have 36 payments, right? And what I notice here is this forms a geometric series. So what I can do is I can use my sum of a geometric series formula to then find out what the value of my savings account will be at time. So, right, it's very important when we're calculating in financial maths, we avoid rounding until the very end to ensure our accuracy. So let's have a look here. John saves $250 a month into an account offering an annual equivalent rate of 5%. How much will he have after 4 years? So what I'm trying to figure out is how much money will he have in 4 years? Well, he'll have all of his €250 payments, right? But then he'll also have the interest that goes along each payment as well. So let's have a look here. So, so we have an annual equivalent rate of 5%. So we're dealing with monthly payments, right? So I need to convert this annual equivalent rate into my monthly rate. So what we do is it's going to be 1.05 is equal to 1 plus I to the power of 12. So this is how much interest I accrue over the entire year, right? And this is my monthly interest rate, and that's 12 months in a year. So if I solve for I here, that should give me what my monthly interest rate is. So the 12th root of 1.05 minus 1 is equal to I. That is equal to 5. So that is equal to roughly 0.40741%, right? I'm giving it a few decimal places just so I'm accurate. So let's form a geometric series. So like I said, right, let's just look at our first installment and our last installment. So my first installment, so how many months is it accruing interest for? Well, there's 4 years. So 4 years times 12 months equals 48. So there is 48 payments. And my first one here, now I'm assuming it's being put in at the start of each month. So my first payment here is going to be 250 times 1, add on my percentage here. So it's going to be 1 plus 0.0040741. Right? My first payment, that accrued interest for 48 months, right? And then my last payment would then only be accruing interest for 1 month. So I have a geometric series here, right? So what first I'm going to do is I'm just going to rewrite this now kind of back to front. So I'm going to start with this one and end with this one. Does it make a difference? No. It's just if I kind of rewrite it now backwards to front, backwards to forwards, it just changes what my common ratio would be. So I have 250 times 1.004074 power 1 plus 250 times 1.004074 to the power 2 dot 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 all up to 250 times 1.004074 the power of 48. Right, so there's my geometric series here. My first term is going to be 250 times 1.004074. My common ratio, well, I'm just multiplying each term by 1.004074. And then my t, my time, or sorry, my n, I should say. My n, how many payments do I have? I'll have 48 payments. So now let's apply my geometric series formula. So if you remember, the sum of a geometric series is a times 1 minus or to the n, all over 1 minus or. So that's going to be 250 times 1.004074 times 1 minus 1.004074. That's to the power of 48. All over 1 minus 1.004074. Have a look here. So if I put this into my calculator, I get 13,277.92. So if he saves 250 a month for 4 years, his savings account, he should have €13,277 at the end of them 4 years. Right? Now let's look at an example of just early repayments. Right? So Mr. Mooney bought his house on January 1st, 1975. Must be nice. He took out a 30-year loan with a monthly payment of 1,260 and an APR, an annual percentage rate of 9.8%. On January 1st, 1995, after 20 years, he decides to pay off the loan. Find the balance of the loan, the amount he owed at that time, i.e., the present value of the last 10 years of payments. So what we're doing here is we are trying to find out. Okay, so he actually he has a loan for 30 years. He then decides on the 20-year mark, it's like, here, I have the money. I'm just going to pay it off now. So what we have to remember is, right, we were looking at future values there. So we're now looking at, well, how much is it right now? You know, if he was to pay it off in 20 years' time. So let's just calculate the monthly interest rate here. So it's going to be 1.098 is equal to 1 plus I to the power of 12. I is equal to the 12th root of 1.098 minus 1, which is 0.007822129. So the remaining payments, right? So it's a monthly repayment. So there's 10 years of 12 months, so 120 payments. There's 120 payments. So let's look at now, we're looking at present value, right? So if you just recall here, what's present value? So remember, F equals P times 1 plus I to the power of T. This P here is my present value. So I can find out, right, my present value. My present value is just my future value divided by P times 1 plus I to the power of T. So what we know here is, though, So my future value of payments, my future value of them payments is just going to be the monthly repayment amount. Like I know in 10 years time, my final payment is going to be, what's in this case, 1,260. I know in 10 years time, my final payment is 1,260. The problem now here lies is, okay, if it is 1,260 10 years from now, how much is that actually right now? Because, like I say, a fiver 10 years ago does not equal a fiver today, right? So the same logic could be applied. Well, the same logic could be applied to, well, a fiver in the future is not going to be worth the same fiver it is today. So let's just calculate the future values, the present values of each of these. So let's look at his first payment will only be accruing interest for 1 month. So it'll be 1,260 all over 1.00782.129. He only gets a payment for 1 month. The next one, 1,260. His second payment was only kind of accruing interest there for like 2 months. Ding, 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 ding. Let's look at the final payment. And the final payment now is 1,260 over 1.00782.129, all to the power of how many payments I have, which is 120. So there's my geometric series. So where A is this term, or is going to be equal to 1 over 1.0072129. And then n is equal to 120. So apply our geometric sum formula. So a times 1 minus or to the n all over 1 minus or. Put this in here. So plug this in to my formula here, like so. And we get the remaining balance to be 97,847.55. So that is how much he is then repaying upfront, right, after 20 years. So he pays off his mortgage for 20 years. On the 28th year, he's like, I'm just paying this off. And how much is he paying off? Well, he's paying off 97,847. Right. I'll leave it there. Right. I hope this video was some help, you guys. And I will catch you guys later. Bye.